Okay, everyone, good afternoon. Welcome to our 10th lecture for the Postgraduate Dynamics course MSD 780. This is also then the second lecture in our optimization and dynamics study theme that we're going to look at. Before we jump into today's application examples, just an overview again of what we did in the previous lecture. We just focused on an introduction to the dynamic queue optimizer that we're going to use for solving our multi-body dynamics parameterization problems. We mentioned that the dynamic queue optimizer is a gradient-based optimizer. So with that, there's some advantages and disadvantages that we need to consider. One of the major advantages of any gradient-based optimizer is its speed. It's able to take very few iterations to solve a problem or to converge to some solution. But it also requires much less inputs compared to some sort of a global optimization technique. Now, with that being said, since it is gradient-based, it tends to rather converge on some sort of a local minimum. And if we're interested in finding the minimum of an objective function, where we're interested in the global optimum, then we either need to focus on a global optimization technique, or we can adjust our dynamic queue optimizer and say, well, let's take different initial guesses. Let's see to what solution each of these initial guesses converge to. And then we simply take the minimum of all of those minimized objective functions, and that will then give us a good idea of where our global optimum lies. And this is also a typical practice and algorithm that is used to overcome the drawbacks of the speed with regards to global optimization techniques. So if you're more interested in optimum design, you can always go and have a look at MATLAB's Simulink and its optimization toolboxes as well. Over there, they delve into a few different ways in which you can go about optimizing your solutions. But for the purposes of MSD 780 and performing optimizations in DAP-BC, the dynamic queue optimizer is more than sufficient. Now today we're going to jump into the integration of optimization into DAP-BC. And for that, we're first going to focus on point 5 in our mind map, which is the optimization procedure that we need to run through whenever we do this type of parametric problem. So expanding over here, you'll see that there are two fundamental steps. The first one deals with the DAP-BC workbench that needs to be updated so that you don't need to give inputs during the process, during each iteration that is being performed. Now you'll remember from DAP-BC, if we simply run the dap.m file, we need to give inputs like whether we want to correct the initial conditions, what our subfolder is that contains all the model files, and it also prints out the initial conditions, and it gives us the number of function evaluations at the end. So we want to mitigate all of that. We want to remove that from the command window so that when we run the optimization, we simply see the iteration number with the parameters at each iteration value or iteration number. So in other words, we just want to see the objective function, the value of the design variables, what happens to the X norm, the RFD, all of those kind of values. Now to do this, we jump into step 1. And it says over here that firstly, under the dap.m script, we need to manually insert the folder name containing the input files, so that the system does not ask for this each time the optimization runs an iteration. So if we look at the dap.m file, you'll notice in line 15, we're going to have that folder equal to input, and then it asks us which folder contains the model. So we don't want the program to ask us for the input, we want to directly stipulate what the folder name is. So to do that, we simply comment out line 15, and in line 16, we then define the actual name of the folder. So in this case, it will be PR_D. We're going to look at the pendulum rod example in point 6 of this mind map. But just take note that we need to manually input the folder name over here. Once this is done, still under the dap.m file, we then comment out the initial condition correction input line. And this is then line 24. So over there, answer equal to input. So we need to specify Y or N on whether we want to correct the initial conditions. As we know by now, it's good practice for complex multi-body systems to always correct the initial conditions just to make sure that there's continuity across our mechanism. So instead, we comment out line 24 and we add line 25, which simply says answer is equal to y. Then still under DAP, we manually input the final time and the time step values as well. Previously, we once again gave these as user inputs. We want to completely eliminate that so that we just give it as stock standard values that are going to remain the same as we perform the optimization. So to do this, we comment out lines 39 and line 46, and we manually type in T final and DT, which is then the final time and the reporting time step. And then we also comment out the last two lines in DAP.m to suppress the display of the number of function evaluations. So line 53 and 54, just make sure that we don't print that out and we have proper continuity when we print out that optimization table to the command window. And then we also comment out the corrected initial conditions output under the formulation analysis IC_correct.m script. Okay, so let's quickly try and implement this then. If I go over to Octave, then I need to go and open the DAP BC Dynamic Queue Hybrid Workbench. This is the workbench that we started off using in the previous lecture. Today we're just going to work in the main folder. So if I navigate to my computer where I stored that, I can now head to DAP BC Workbench material, and then I have this DAP BC Dynamic Queue Hybrid Workbench revision 1 that I'm going to use. So I double click on that, double click again, and now I'm in the main folder. And this is where I'm going to work whenever I perform the combined dynamic and optimization analyses. So I simply choose this directory over here, and now I can start making the changes. So if I head into DAP.m and I zoom in a bit, you'll see that line 15 is now still uncommented, so it still says folder is equal to input. We're simply going to comment that out, so I'm going to hit Control and R on my keyboard, and then I can uncomment line 16, so Control, Shift, and R. Okay, so that now gives the folder value as an explicit string as input. Then I also need to change my input for the correction of the initial condition. So to do this, I Control R line 24 and I Control Shift R on line 25. And now that's also a constant input that I give. Then for the final time and DT, I'm going to do exactly the same. So comment out line 14, uncomment line 41, and then comment out line 47 and uncomment line 48. And then finally lines 54 and 55 I'm going to comment out, so I select them, Control R, and these are then all of the changes that I wanted to make to the DAP.m file. Next, I now have to head to Formulation Analysis IC_correct. Okay, and in this case I already commented it out, but if you open it, it might look something like this where it's uncommented. So this just prints out the corrected coordinates once you've done the initial condition correction. We trust in the process that is being followed by DAP BC, so we don't need to print that out for every iteration that the optimizer goes through. So instead, I simply select lines 47 to 54 and I hit Control R to comment that out. Okay, so now nothing will be asked of me during the optimization. All of the inputs are given in the script. So the only thing that I need to worry about is monitoring what happens at each iteration of the optimization, which is going to be printed out to the command window. Okay, and that then is also step 1 that we wanted to look at over here. So modifying the DAP BC workbench. Next up, we can now start looking at the actual procedure that we're going to follow in order to solve some sort of an optimization problem. So to do this, if I expand over here, firstly, we always want to identify the parameter that we want to minimize or maximize. And this will define your objective function. Once we've done this, we need to also identify the parameters that will influence the optimization, and these are known as the design variables. So variables in the sense that it doesn't have a fixed solution, or you give some initial solution, but it doesn't necessarily mean that that is the optimum. changing these variables will affect how the objective function is going to behave. And then step 3 simply says that whenever we work in the DAP-BC model files, we need to assign the variable number to each of the design variables. And we name them xdap1, xdap2 up to xdapn, where n is the number of design variables that we have. So important thing to remember over here is whenever we work in the DAP-BC model files, we don't just say x1, x2, we use x_dap. Right, and that is just to make sure that there's a continuity between the DAP-BC model files, and then once we move over to FCH and grad FCH and all of the files that are stored under dynamic queue, that these two systems or these two variables can talk to one another. Then in step 4, we make sure that the vector xdap is defined globally under the formulation sum files include global script. All right, so if I go back to Octave over here, you'll see that if we once again go to formulation, we expand some files and we open up include global, you'll see that the first line over here says global xdap. So this just makes sure that we globalize the xdap variable or the xdap vector so that it can be used by the dynamic queue scripts as well. It's just a quick check that you can do before you start with your optimization, just to make sure that your variables are defined in the correct workspace. And once this is done, we then define any constraints, whether it be inequality, equality, or boundary constraints that may be imposed on the data or the variables. We then define a new script and a function which takes in the relevant design variables and outputs the function and constraint values. So this we will refer to as well as a transition script, in the sense that it takes all of the outputs that you got from the post processor of DAP-BC and it prepares it to be used within fch.m or grad fch.m, which are the two dynamic queue scripts that we're going to work with. Now, speaking of that, we can then head to the dynamic queue folder and we update fch and grad fch.m we first update fch.m by putting in the objective function, the inequality constraint, and the equality constraints, and then in grad fch.m we can use some sort of a finite different approach to define the gradient. Now remember that from the previous lecture we had analytical functions, so it wasn't too difficult for us to set up the Hessian matrices or the gradient matrices within grad fch. But in the case of using something like DAP-BC, we know that if we want to find something like the maximum acceleration of a mechanism or the maximum speed or the maximum reaction force, these type of things are not calculated explicitly in terms of the design variables. Instead, it uses the design variables together with the mass of the system or the moment of inertia of the system or any other parameters to give us a proper calculation and an implicit calculation of the kinematics and the dynamics of the system. So in that case, we need to make use of some sort of a finite difference approach, since the analytical equations are not readily available. The only thing that we need to model over here and that we need to take into account is this delt x. And a typical value for delt x is 10 to the power of -8. This is usually, from a sensitivity analysis perspective, also a good value to use when calculating the localized gradient at each objective situation or each objective iteration. And it ensures that the gradient is local enough so that DAP-BC or the dynamic queue optimizer is able to sufficiently converge towards a local minimum. Now in step 9, in the main folder, we also update the optimization.m script to include any starting points, lower and upper boundary conditions, and any other inputs that are not at default. So optimization.m is simply your final script. This is where you group all of the inputs to the dynamic queue optimizer in. So as they mentioned over here, you give the starting points, the lower and upper boundary conditions, and then if you have some tolerances on the step size or on the objective function, you can also specify them in this grouped or combined optimization.m script. And once all of this is done, then we're ready to execute the optimization.m script and we can wait for it to run. And depending on the number of variables, the dynamic complexity, and the initial values, the computational time and effort may vary. Okay, so that is just stepwise what we're going to do for today's example. So without further ado, I'm going to jump into the application examples and the very first example that we want to look at as well. So this is the driven pendulum rod subjected to a constant torque. Now you'll remember from our previous lectures, this was PR_D that we looked at, where we provide the system with some sort of a constant torque under the enforces.m script. So today we're simply going to take all of those input or model files and we're going to start parameterizing them. We're going to look at what parameters we can induce on the system. Is there some sort of an objective function that we can get out, and how will the objective function be influenced by each of these design variables? Now to do that, we just quickly remind ourselves of what the driven pendulum rod PRD looked like. Simply had a pendulum rod which was connected to ground via a revolute joint. On ground itself we had point 1, and this was located at the origin of the ground. And then points 2 and 3 were specified on the pendulum rod itself. Points 1 and 2 formed the connection of the revolute joint, and point 3 was simply added for illustrative purposes or to show you the entire length of the pendulum rod. Okay, and then we have the xi eta local coordinate system of the pendulum rod as well, xi being in the direction of the longitudinal axis of the pendulum rod and eta being perpendicular to the rod. All right, now for the forward dynamics problem, we went one step further and we simply said, well, if we break up the system into its free body diagram, this is essentially what we end up with. But the important thing over here is that we applied some sort of a constant torque to this system. And we saw from the calculations that we performed and the simulation, the DAP-BC simulation, that even though we specify a constant torque on this system, the maximum acceleration of the system continued to increase. So a constant torque did not, in effect, cause a constant acceleration on the system. And we can now start utilizing this and asking questions around what happens to the kinematics of the system based on the torque. So if we expand this problem, we ask some design questions. We can say, well, what is the maximum reasonable acceleration the pendulum rod can achieve? How does the initial orientation of the rod influence this value? What is the influence of the constant torque on the acceleration? What would happen if we vary the mass of the system, and how does the pendulum rod's length influence the kinematics of the system? And the nice thing about the dynamic Q optimizer is that we can answer all of these design questions by simultaneously investigating the effect of each of these variables on the objective function. You'll remember from the previous lecture as well, some of the examples that we looked at. We started with a fairly straightforward or single variable analysis of a curve. So f of x is equal to some sort of a function. Then from there, we expanded it to start looking at f as a function of x and y. So now we have two variables. And our final example was a case where we considered four design variables in the system. So in that case, we weren't able to quantify the multidimensionality of the system graphically. We instead needed to rely on some sort of an optimum design approach to lead us to what the minimum solution was. Okay, but that shows us that the dynamic Q optimizer is able to handle a bunch of design variables which may all have an influence on the objective function, and we're going to utilize that today within DAP-BC. Okay, so using all of these questions, we can now formulate a design problem. So we say we want to maximize the acceleration of the pendulum body 1, subject to the starting angle, the constant torque, the mass of the pendulum rod, as well as the length of the rod. So we can already get some of the information for our optimization steps from this first sentence that we have over here. Now, firstly, we say that we want to maximize the acceleration. So since this is some sort of a maximization or minimization, whatever we want to maximize or minimize is going to be the objective function. In this case, it's going to be the acceleration that we want to maximize. And also remember that we said, although we specify the dynamic Q formulation as minimizing some sort of an objective function, if we want to maximize an objective function, we simply take the objective function and we multiply it by -1. And then we essentially reflect the graph about the x-axis, so we end up with a minimization problem. And then we just have to remember at the end to multiply by -1 again to get our actual acceleration that has been maximized. Okay, and then we also said it's subject to the starting angle, the torque, mass of the rod, and length of the rod. So these are all the design variables. These are all going to have an effect on the acceleration of the system. So therefore, we need to assign some variable index to each of them. In this case, we have 1, 2, 3, 4 design variables that we're going to consider. Then we have a few design considerations as well, which are added in tandem with our definition that we gave to the design questions. The maximum time over which the acceleration may occur is 3 seconds, and we need to use a reporting time step of 1 millisecond. The starting angle may vary between -pi and pi, so that gives us the lower and the upper bound of the starting angle. The torque may vary between 3 and 10 Newton meters, so once again, lower and upper bound. And then we also have the mass of the pendulum rod that should be between 2 and 4 kilograms, a lower and an upper bound on that design variable as well. Then we also say that the moment of inertia should remain unchanged at J equal to 1/12 ml squared, which is the standard equation that we use for the type of pendulum rod that we're working with. But this must be equal to 0.06 kilogram meter squared. And the important thing to notice over here is that we say the moment of inertia must be equal to this value. So this tells us that we're working with an equality constraint. Some sort of function needs to be equal to 0 at the end. That is the form in which we provided to dynamic Q. So it's fairly easy to set up this equality constraint. We simply say that it becomes 1/12 ml squared minus 0.06 is then equal to 0. And that is then correctly formed for input into dynamic Q. And finally, the maximum velocity magnitude should be equal to 20 meters per second. Once again, we say something should be equal to some sort of a value. So therefore, this is now a second equality constraint that we specify on the system. And we can formulate this again by saying, well, if we consider the maximum velocity magnitude, we can simply call this the maximum speed of the pendulum rod. And if we denoted V1 max, we can simply say V1 max minus 20 must be equal to 0. And that is then in the correct form for dynamic Q as well. Okay, now with that being said, we can jump into the optimization procedure and we can go through it stepwise and update all of our scripts in order for this problem to run. So let's first start with the actual objective function definition. Now remember that the objective function is the acceleration of the pendulum rod. Since they don't specify the x or y acceleration in this case, we can assume that they're referring to the actual magnitude of the acceleration that we want to go and work out. So where do we get this acceleration from? Well, we first need to perform some sort of a calculation within DAP-BC. Once DAP-BC has run and we've run the post-processor, then we get the answer to this acceleration. This is an output to the DAP-BC analysis. All right, so jumping over to our Octave environment over here, we need to understand that since we get this maximum acceleration after the post-processor has run, we can go into post.m and we can actually go and provide our values over here. So once post has run, at the end we can just add a line to calculate the maximum acceleration value. So that will be denoted as max ACC val, and you can give it your own name if you're running the variables on your side as well. You can call it maybe just max ACC or whatever whatever works for you, as long as you just make sure that you're working with the same variable across all of your scripts. In my case, I'm just going to call it max ACC val to indicate I'm working with a maximum acceleration value. Now, if I calculate the acceleration magnitude, that will be, according to Pythagoras, just the square root of ax squared plus ay squared. So I can just say, well, let's use the square root, and you'll remember that from our post-processor, the accelerations vector that we get is RDD. I'm going to calculate it for all time steps. It's for body 1 in the one direction, so that is AX, and I just say dot square. The dot indicates that I'm working with element-wise squaring, so it squares each element within this array or within this vector separate from one another, and that is exactly what I want. So I'm just going to continue then, and I'm also going to type in plus RDD, once again for body 1, but now in the 2 direction, so that I'm considering AY. Dot squared again, and I can just close my bracket. But this value is now going to give me an entire vector of values that I'm going to get out. Remember that it's element-wise squaring and element-wise addition of each of these vector values. So in order to extract the maximum acceleration value, I simply add max at the start of the argument. I just close the bracket at the end, and I hit the semicolon as well, just to make sure that it doesn't print out to the command window every time I run this problem. Okay, so then I've now formulated the maximum acceleration value and the objective function within the post-processor. So if I'm happy with that, I can then move over to the next step, which is the design variable identification. So we now know what the design variables are over here. We just need to give them a proper index when we refer to them within DAP-BC or within dynamic queue. So what I'm going to do is I'm setting up a vector over here, x1, x2, x3, and x4, and they equate to each of the parameters that I specified on the system. So x1 is the starting angle of the pendulum rod, x2 is the constant torque that I'm going to specify on the system, x3 is the mass of the pendulum rod, and x4 is then the length of the rod as well. Now with this defined, I can now go and update the relevant DAP-BC model files as well. So let's start off with our model folder, which we said is under models. We're working with PR_D in this case. Okay, and I just need to make sure as well, if I go to dap.m, that I define my folder that I'm working in as PR_D, so that's fine. It's going to extract the model files from the correct folder over here. I am correcting the initial condition, so that's fine. My final time from the inputs or the design questions that were asked is 3 seconds, so that's also alright, and then dt is 1 millisecond, so that's also fine. All of the inputs that I needed to provide under dap.m is correct, so now I can move on to the actual PR_D model folders. Alright, so we're not going to worry too much about inAnimate. We're not going to do any animations during the optimization, so we can leave this script as is. Instead, we're going to jump into inBodies. Alright, now body1.n is one of the design variables that we need to change. Remember that we said we want to change the mass of the pendulum rod and see what the effect of that is on the maximum acceleration. And since I'm working in one of the DAP-BC model files, I need to remember that if I specify the design variable in this case, I use _DAP. And that is now what I do over here in line 5. So I say that body1.n is now no longer a constant value. It's now a design variable. And I simply call this xdap3. And this corresponds to what I gave here as input. So x3 is m1. So x3 is the mass of the pendulum rod. So I call that xdap3. Then the moment of inertia of the pendulum rod, we know is also given by this equation over here, 1/12 ml squared. But m and l are both design variables. So m is x3 and L is x4. So if I want to go and write the moment of inertia of body 1 or of the pendulum rod, then it becomes 1 over 12 x dap 3 multiplied by x dap 4 squared. And I simply write it accordingly in the in-bodies input file. Then the starting angle is one of the other parameters that I need to give in, and this is x1, so the first design variable. So therefore, I just have to go and say b1.p is equal to x dap 1. And then finally, I need to now consider the dependencies of the other parameters on each of these design variables that I specified. And one of them is the location of the center of mass of body 1. Now to do this, I can go back to this model that I had over here, and maybe rather this one, which shows the angle as well. So we have the starting angle available. We want to find what the initial coordinates, the x and y coordinates of the pendulum rod is. So if I look at this and I simply use trigonometric relations, then the x coordinate will be L over 2 multiplied by cosine phi 1, and the y coordinate will be L over 2 sine phi 1. L over 2 is simply written as x dap 4 over 2, since L is going to be a design variable, so it becomes x dap 4 over 2 multiplied by cosine, and phi 1 is then x dap 1, because that's the other design variable that we have. And I simply do this then for the x and y coordinates so that I can write them in this form over here. So this 0.5 multiplied by x dap 4 is simply L over 2 multiplied by cosine phi 1. And phi 1 being a design variable just becomes x dap 1. I do exactly the same in the y direction. So that is just L over 2 multiplied by sine of phi 1, just parameterized in accordance with the indexes that I gave to each of the design variables. Okay. Right, so with that then being done, we can move over to our next input file, which is in forces. So if I open this one up, you'll see that originally we had S1 as a force structure. The type was weight, so we don't have to worry about changing that. But the second force structure that we have over here is the constant torque that we specified on the system. And before we made the changes, this was simply denoted as S2.T, which is equal to 6.0, meaning we specify a constant 6 Newton meters torque on the system. But the torque is one of the design variables, so we need to go and update this in forces as well. So torque is x2, or in the case that we're working with a DAP input file, it's simply x underscore DAP 2. Okay, so now I've parameterized the torque of the system as well. Then in funct is an open list, so we don't have to change anything over here. In joints simply specifies the revolute joint of the system between point 1 and 2, so we don't have to change anything with regards to the joints. The joint structure remains the same. However, we need to go over to in points, and we need to consider what we had over here. So point 1 was located on body 0, on ground, at the origin of the global coordinate system. Nothing really changes over here. But because the length of the pendulum rod is going to change, the location of points 2 and 3 relative to the center of mass is also going to change. If I look back at the system that I have over here, you'll see that point 2 and point 3, which are specified on the pendulum rod, their location relative to this center of mass, or this local coordinate system over here, is going to change based on this value over here, which is now 0.3, but it's actually L over 2. It's a parameterized property of the system that I now have. So I just need to go and update point 2 so that its local coordinate system, or local coordinate, will be minus x dap 4 over 2, and point 3 will be x dap 4 over 2. So just making sure that I specified as minus L over 2 and L over 2. And that is then exactly what I do over here for the xi direction of each of these points. the eta direction remains unchanged because the 2 points are in line with the xi axis. Right, and then finally, I can also have a look at in U vectors, which is also an open list, so there's no need for me to change anything over here. Okay, and that is then all of the properties that I wanted to change for the DAP-BC model files. Now, before I move over to step 4, I just want to open the floor for any questions at this stage. Are there any questions with the parameterization that we've done thus far? Okay, I don't see any questions, but you're more than welcome to post a question under the chat messages, and then I will get to you. Okay, so for step 4, XDAP is defined globally under formulation some files include global. This is just something that we need to go and double check, and we double checked it previously, but let's just perhaps triple check it. So if I close include global over here, we just need to remember where we find it. So it's under formulation some files and include global. And over here I now have global XDAP. So that ensures that all of those XDAP design variables that I've now specified under the model files are now going to be translated to dynamic queue and to the transition script so that I can use them throughout or universally across all of the scripts. Whether I'm working in a dynamic queue script or a DAP-BC script, it doesn't matter. And now I can start defining the constraint functions required to limit the design parameters. So firstly, we need to specify the maximum velocity magnitude, and this we can define directly under post.m. Remember that the maximum speed of the system is also found after the post processor has run for DAP-BC. So I can go ahead and navigate to post.m. And once all of the post-processing has done, I've now calculated the objective function, but I now also calculate any other parameters or any other function values that I need for my equality or inequality constraints. So let's start with the max speed value. Simply going to call this max speed val, and I can use more or less the same definition as what I had previously. So I'm just going to Control-C, Control-V, copy these values over. And then since I'm working with the speed values, I just drop one of the D letters over here so that I just end up using RD, which is then the annotation that I use when I want to get the maximum speed values or the speed values from DAP-BC. Okay, now that that is done, now I can go and define the general formulations for each of my equality constraints. So let's first focus on H1, which is the first equality constraint. But what's interesting about this equality constraint is V1 max is not a design variable on its own. The value of V1 max is calculated post-process. So after DAP-BC has run, then I only get the value of V1 max. I don't have an explicit formula in terms of the starting angle and the constant torque and the length and the mass of the rod. I need to rely on all of the steps that are being performed within DAP-BC before I can get the answer of V1 max out. So this is in fact an implicit version of an equality constraint, and instead of directly specifying it under fch.m, I can define it under a transition script, which we're going to look at in just a moment. But just take note that this is not explicitly in terms of the design variables, and that's why we can specify it under the transition script directly. But what we said previously was that the maximum speed of the pendulum rod must be equal to 20 meters per second. Then in the case of H2, which is then the second equality constraint, if we look at its form, which is 1/12 ml squared, if I go and substitute the values in for x3 or for the mass and the length of the pendulum rod, then I end up with 1/12 x3 times x4 squared, which must be equal to 0.06 kilogram meter squared. So this equality constraint is in fact given explicitly in terms of the design variables. I don't need to first go through DAP-BC and do the calculation before I can set up the equality constraint. I can directly formulate it in terms of the design variables. And for this reason, I'm going to specify this h2 as a function of x directly under fch.m. Then in addition to that, I just specify the lower and upper bounds on the system as well. So these are also given from the design considerations. The first column over here indicates the design variable that I'm working with. So the starting angle, this was the constant torque, and then the mass of the pendulum rod. And each of them have values minus pi, 3, and 2 for the lower bounds. And for the upper bounds as well, starting angle, constant torque, and mass of the system or mass of the pendulum rod, and their upper bounds are pi, 10, and 4. And these low and up vectors I'm going to formulate directly under the optimization.m script. Alright, so jumping over to step 6, which is now the minimizer input script. And this is a new script that we haven't worked with yet, which is also known as the transition script. This takes in all of the outputs that we got from DAP-BC and prepares them to be used for the fch.m dynamic queue script. So it's created under the main folder to combine the objective function and the constraint values, which are based on data outputs. And what we do over here is the first line, we just say add path gen path formulation. So this just generalizes the path that is used by all of the formulas for DAP-BC. Then we also have this line include global. So this runs that include global script over here and make sure that we globalize all of our relevant variables. One of those variables, of course, being xDAP. And that is then line 5, where we simply say xDAP is equal to val. So this is just standard just to make sure that we combine the input argument of minimizer inputs with the actual design variables that we specified in DAP-BC. So lines 3 to 5, you don't have to worry about changing. Lines 6 and 7 are also standard. These just run DAP and post, so they run the actual DAP-BC workbench so that we can get the relevant outputs. But now the lines that we need to change are lines 8 and 9, where we specify constraints. We specify them afterwards. So let's perhaps quickly go back, and I'm just going to close some of these scripts just to free up some space. If I now head down to minimizer inputs over here, okay, so we can see lines 3, 4, and 5 remain as is. Lines 6 and 7 we're not going to touch, but now we need to specify the objective function, and we remember that h1 is also implicitly defined. So we can define those two properties under the minimizer inputs script over here. So we start by seeing that if we look at the function, the outputs that we need to get is the objective function and h1. So I'm just going to call this objective function equal to, and now my objective function, if I remember correctly from post.m, is going to be max ACC val. So I'm going to take this value over here, and I'm just going to paste it over here. Right, so now I've ensured that my variables match up across the two scripts, so that's fine. Now, something that I also need to take into account is that I'm working with a maximization problem. So in order to perform a maximization problem, I take my objective function and I multiply it by -1. So I just have to do that over here, -1 times maximum acceleration value. And now instead of performing a minimization problem, I'm now going to perform a maximization problem on the acceleration. Okay, and then next I specify h1, which is my implicit equality constraint. If I look back at post.m, I defined the maximum speed as max speed val, so I'm just going to copy its name over. And this value must be equal to 20, but in terms of dynamic queue, I need to write it equal to 0. So it simply becomes the maximum speed value minus 20. Which is then equal to 0. Okay, so now I've defined all of my implicit outputs that I got from that PC. If I'm now happy with that, I can now move over to the fch.m domain and the script as well. And for that, I then head over here to dynamic queue. I'm still going to remain in the main folder. I'm just going to expand this drop-down menu over here, and now I can go to fch.m, which is this file over here. I double-click on that one. It opens up fch, and now I just need to scroll down to where I need to specify the objective function and also any equality constraints in the system. So to do this, I'm just going to say over here, let's call it objective function, comma h1, which is then equal to minimizer inputs. And in this case, the inputs that I give, and since I'm working now in one of the dynamic queue files, is not going to be xdap, but it's instead just going to be x that I specify. Okay, so now I'm getting the objective function value and I'm getting h1. Now I just need to go and say, well, f is the actual annotation that I need to use for the objective function. So f is going to be equal to objective function, and then my first equality constraint h1, which is then indexed in parentheses, is equal to the h1 value that I got from the minimizer inputs. And now we can specify h2, and we specify it directly under fch.m since it's explicitly given in terms of the design variables. So if I quickly check back over here, we said h2 is 1 over 12 x3 x4 squared minus 0.06. So I just go and type this in as 1 over 12 multiplied by x3 multiplied by x4 squared minus 0.06. Okay, and now I've specified both of my equality constraints as well and my objective function. So now everything should be defined correctly. If I now scroll down, step 8 requires that I just go to grad_fch.m and I use some sort of a finite difference method to calculate the gradient or the Hessian matrices of the system. For this problem, I'm just going to use the standard delt x equal to 10 to the negative 8 value, which is deemed appropriate for this problem and for most of the problems. If you're interested in how we actually get these values, there are some studies on sensitivity analyses and how you can check what the sensitivity of that step size is to the calculation of the gradient and to the convergence of the dynamic queue optimizer to a solution. But for our intents and purposes, we will either give you the delt x value, or if we don't give it, you can assume to work with 10 to the negative 8 in any case. Okay, so I go to grad_fch.m over here, and if I scroll down, you'll see that the finite difference interval that is uncommented. So there are two finite difference methods over here. The first one is xi plus delt x. So this is the forward difference method that I use, and it's a good method to actually go and calculate the gradient. So it simply takes the current objective function and then steps it one level to the right and calculates the finite difference or the gradient in that manner. The central difference method is going to take a bit longer because it requires an additional function evaluation to be performed based on each design variable. So in that case, it takes one step forward and one step back, and it calculates essentially the average gradient based on those two values surrounding the objective function. But for our purposes, the forward difference method works quite well. So we're going to stick with this method for this problem that we want to solve. Okay, and I can just make sure that I'm working with delt x equal to 10 to the negative 8. So 1.d minus 8 is just another manner in which we can write 10 to the negative 8. So I'm happy with this, and I know that the system is going to be able to use the forward difference method since I commented out everything else. Okay, and then I can move over to optimization.m. And like we said, this is the script that combines all of the boundary conditions, all of the starting configurations, all of the convergence tolerances that we want to specify on the system. So this is the last script that I'm going to modify. And this is also the script that I'm then going to run in the command window. And you'll find this under the main folder. So you'll see optimization.m over here. If you double click on that one, it opens up what I have over here. So firstly, we start in lines 1 to 3 by just clearing the workspace, closing any graphs that are open in the background, and also clearing the command window. And then for those who are interested in the actual optimization runtime, we just initialize tick over here, and then at the end, we say runtime is equal to toc. So whatever happens between these tick, toc keywords is going to be the optimization runtime required to perform this analysis. And then at the end, it will also print out what the optimization runtime is. And you can go and compare for different mechanical systems, different complexities, what happens to the optimization runtime, and how does it compare with your expectations based on the function evaluations within DAP-BC. Okay, but with that being said, we then also have add path, gen path, dynamic queue. So we now just add dynamic queue to our folded paths, just to make sure that all of the folders and all of the files that we're working with are universal. Add path, gen path formulation is then also added. Once again, all of the formulation files are then universalized. Then we have include global, which globalizes all of the variables in the system. And now I can go and list all of the input or initial conditions that I want to give to each of the design variables. And this is from line 9 to 12. Now, of course, if you have 5 or 6 different design variables, you just update them below this. So you can say x5 is equal to some sort of a value, x6 is equal to some sort of a value, and so forth, depending on the number of design variables that you have. Now, in our case, we're just working with 4 design variables. And the values over here have just been assumed for this study. In the case of an exam question, we will in any case give you the starting configuration or the starting conditions. So we will say x1 is equal to this, x2 is equal to this, all the way through for all of the different design variables. And you can simply plug them in and see what happens based on that starting configuration. Okay, but in this case, these are the values that we can assume are given to us. And then we have to just group them together in this x0 list or vector that we have over here. So we simply write them out x1, x2, x3, x4. So you just have to remember that if you now have x5, x6 over here, you just need to add them to this list as well. So you can just say x5, x6 over here as well. Okay, but now in our case, we just work with 4 design variables. So I'm just going to delete this. Okay, and then we also need to give the lower and the upper bounds with regards to the different design variables that have been given to us. So for the lower bounds, we just go back to our mind map, and they were listed over here. So column 1 is 1, 2, 3, so the different design variables, and then we have minus pi, 3, and 2. So I've just written it over here. So 1 minus pi, 2, 3.0, and then 3 is 2. And then for the upper bounds, 1, 2, and 3 are pi, 10, and 4 that we assign over there. Okay, and then I can also set up the actual dinq command to run in this line over here. So I simply call xf. So this ensures that the optimized design variables will be stored in the variable x, and f will contain the minimized objective function. And this should be equal to dinq. So the inputs that I give in this case is the starting coordinates, the lower bounds, the upper bounds, and then for this problem I can assume to work with a move limit of 1, which is fine. And we also have a convergence that is specified on the step size and also on the objective function. So the objective function value is in any case default 10 to the negative 8. I'm just specifying it over here just to show you the, the order in which we specify each of these arguments. And then the convergence tolerance on the step size has been made a bit looser. It's now 10 to the negative 3, where the standard default value is 10 to the negative 5. Okay, so then I have runtime, and it will print out the runtime as well at the end. Okay, so if I'm happy with all of that, I simply go over to my command window. Over here, I can also type in clear all, close all CLC if I want to, and then I can type in optimization, and it will run the optimization script. So if I hit enter, it should clear the command window completely. And now it's going to take a bit of time to run each of these function evaluations and to print out the different iterations for each problem. Now, I've gone ahead and printed out the values over here in the step 10 as well. Sorry, just a all right, sorry about that. So in step 10, I've just printed out the values that we actually get from the command window. In total, we can see that it took about 23 iterations to converge to a solution. Now, what I believe this was in one of the previous versions of Octave that I got this result. With the latest stable version, which is version 10.2.0 that I have of Octave installed over here, I got slightly different results, and I also think I plotted them out somewhere. I just have to check where. All right, I'll just have to double check, but I think for the current version, the optimization convergence was a bit better. It converged after about 17 iterations, but the time it took to reach the solution was about 46 minutes. So the same as what we required over here in one of the previous releases. So it took quite a bit of time to run this problem. And we can understand why, because the function evaluations are definitely not trivial. We applied 4 design variables to this problem, which means it's a fairly large multi-dimensional problem. And we need to understand that when we provide or do some sort of a gradient calculation, so when we calculate our Hessian matrices, we not only consider the single objective function evaluation, but for each design variable, we also perform an additional function evaluation, so that it's able to find the gradient in all of the different directions corresponding to each of the different design variables. So it took about 46 minutes or 3/4 of an hour to run this problem. But the results that we got out over here then shows that the optimized design variables are 0.179, which is the radiance value that we got for the starting angle of the pendulum rod. Then we have 8.94 Newton meters of constant torque. We then have 4 kilograms for the mass of the pendulum rod, and 0.4243 meters for the length of the pendulum rod. And if we apply all of these, the resulting objective function value that we get is minus 1,887. Now with the latest run that I got, I found a value of about minus 1,900. So the values do correspond to some extent. Of course, it just took now a bit less iterations to run for the latest version of Octave. But you're more than welcome to go and run this problem on your own and see if you get more or less the same results as well. What's interesting to note over here is if we look at the X norm values, we can see that we started with 10 to the negative 1, then it went over to negative 2, negative 3, and then over here at the end we have negative 3 to negative 4. So there seems to be some convergence that we can also list if we look at the histories of each of these plots. So if I perhaps zoom out a bit, There we go. If we look at the objective function history, we can see that initially it starts at minus 250,000, but then after some time it plateaus over here at the end as well. So relative to this minus 250,000, it looks like there's not a lot of variation, but if we go into the results over here, we can see that all of them are around 10 to the negative 3. 10 to the power of 3, just minus 1,900, minus 1,996. So these values indicate that it wasn't able to achieve that initial very small acceleration of the system, but due to the constraints of the system, it plateaued at a higher objective function value, but it was able to then specify or adhere to all of the constraints of the system. Okay, so if we go down to the variable history, we can also see that after about 20 iterations, so iterations 20 to 23, we can see that there's a plateau in the value of the variables as well. So this is also then where we see convergence. We can see from 21 up to 23, we have -3, -3, -4, based on the X norm values. And then if we look at the lower limit inequality constraints, the upper limit inequality constraints, we can see that all of them are below 0 as well, which is fine. And then if we go to the equality constraints history, we can see that for one of the equality constraints, we can see this oscillatory effects that we have over here, but after about 20 iterations, it now settles on the 0 line. And that's always what we want to see when we deal with equality constraints. It has to be very close to that 0 line, since whatever our equality constraint is, it needs to be equal to 0 at the end. All right. So these are then the graphical outputs that we get from the optimization.m script if we run that. And this is then also the first example that we wanted to look at in this case. Now, once you're happy with all of the results, you can actually go and plot it inside DAP-BC, and I'll leave that to you as an exercise. But what you can do is, if you have all of these values, you can simply go over to your command window after you've now said clear all, close all CLC. Then you can say, okay, so let's say xdap is now equal to all of those inputs that I had over here. So 0.179, 0.179. Then I have 8.9378, 8.9378, uh, 4 and 0.4243. So 4 and 0.4243. Okay, so now I've specified all of these values over here. So xdap is loaded. If I'm happy with that, I can now simply say dap. And because we haven't globalized or run include global at this stage, it will just give you a warning that xdap is defined in the current scope, but in a future version, global variables must be declared before use. You don't have to worry too much about the actual warning that you get over here. But in the case of running an optimization, you in any case run include global first. So you don't have to worry about this. In this case, it's just to do a quick plot and see what happens to the system. So you can then run post. Okay, and once this has run, I can just look at the optimized acceleration curve as well. So to do this, I can just say let's plot against time. We want to plot the square root of RDD for all time steps 1, 1 dot squared. This will be plus RDD for all time steps body 1 in the 2 direction dot squared. think I skipped one of the brackets over here. Let's just do that. Okay, so here we can see that the system starts from rest, and then after 3 seconds we have now reached our maximum acceleration, which is now 1890. If we quickly look back at the results that we got from the optimization, and if I zoom in a bit, you'll see that the value that I got at the end was minus 1887. So there's a bit of a round-off error, but overall I get the same magnitude value. But it's just important to also note that since I'm doing a maximization problem, I had to multiply by -1. So the maximum acceleration that I expect to get out from DAP-BC will be whatever this f value is over here multiplied by -1. I just need to take it back to its original value. So I just multiply by -1 again, and the actual maximized acceleration is then 1890. Okay, and that corresponds well with the graph that I also plotted out over here. Okay, and then if I want to, I can also check the optimized speed curve just to make sure that my velocity magnitude at the end is indeed 20 meters per second. So to do this, I can simply take away the last letter D over here, so that I just end up with RD, which is then the formulation for the speed. So if I hit enter, I can see that my 20 meters per second mark is over here, and after 3 seconds I end at 20 meters per second. So my maximum speed value equality constraint of 20 meters per second is also met in this case. And then finally, if you want to, you can also go and have a look at the initial configuration. So you can just run the animation and see what that looks like. So we can see it starts at some positive angle over here. I'm not going to run it now, but you're more than welcome to have a look at that in your own time as well. Okay, so we can see in this case that the DAP-BC results correspond well with the dynamic Q results that I got for the optimized mechanism. All of the equality constraints have been met, so my solution is maximized and I have met all of the constraints of the system, and I'm happy with the solution that I got. And that then also concludes our fifth application example that we wanted to look at for this lecture. So with that in mind, are there any questions before we end off for today? Okay. If you are typing a question, just in the meantime, next week's lecture will be hosted by, will be a guest lecture. So the gentleman from Simtech Engineering will be joining us to talk a bit about MSC atoms and the use of multi-body dynamics within the atoms domain. So it's going to give you a bit of an overview of what you can expect within the commercial environment, where you now have access to some sort of a user interface-based design of multi-body dynamics and how you can solve the problems over there. But I will also post an announcement closer to the time just to give you an overview of what we will be discussing, and I believe we will also be making available access to the Atoms the Atoms Student Edition that you can download and follow along with during next week's lecture. Okay, but with that being said, and I don't see any questions, I'm then going to end it off over here, and I will then see you again next week. Thank you very much.